So here's another proof where we'll look at a longest path in the graph. This one's pretty similar to the one we did in class, but it has a few differences. So like we had in class, we're looking at a graph with minimum degree k. That is, every vertex has degree at least k. Then the claim is the graph contains a cycle of length at least k plus 1. Or in other words, G has a cycle Cn, and that n is greater than or equal to k plus 1. So this is a little different from the path question, because if you have a long path, right, like a pk plus 1, you definitely have any smaller path. But that's not true with cycles, right? If you have a C5 in the graph, you might not have a C3. So we have to be a little careful about that. But our proof will turn out fine anyway. So like I said, we're going to use the strategy of looking at a longest path, right? So G definitely has a longest path P, so let P be a longest path in G. Some stuff happens in here. So here's our path P. It has two end vertices. Here's U, and here's V. But it turns out we really only care about U. So let's just look at U. Okay, so now we're going to sort of turn all our attention to U. So here's U. It has some neighbors, right? Vertices that it's adjacent to. And we're assuming that every vertex has degree at least k, right? So U has at least k neighbors. Now, what we proved in class was every neighbor of U is in the path. Okay. But U can't have an edge to all those vertices in the path, because then it wouldn't be a path. So one of these U does have an edge to. Let's say it's this one. And all the others are somewhere in the path that winds around. And if we travel from U, one of them must be last in this path. So let's say it's this one, and it's W. Right? Whichever neighbor sort of comes furthest away from U in the path. Well, now we're going to add in an edge. Right? W is a neighbor of U, so there's an edge there. So let's grab that edge. And now we have a cycle. Well, what's the length of this cycle? It contains U and all of U's neighbors. Right? U is 1. There are k of those. So we have a cycle of length at least k plus 1. Right? There might be other vertices in there. So that's a little more specific, right? A cycle of length n where n is at least k plus 1. And that's what we wanted to prove. So we're done.